везти в лабораторию у Утона,
Да.
да? Вот, ну, Утон же 4-й месяц уже болеет. Что-то там серьезно похоже. До сих пор был больничный.
Я знаю.
Как он принимает это, загружайте.
Да. Делать мне больше нечего. Так. Bergens, Schmergens, це туди вишено. Rainy days, rainy days. Come on, machine, move up. Input socket. Oops. The switch. Oh, hello, Professor. Come on. Oh, so many messages. Okay, okay, welcome, welcome. Welcome, welcome. 1 minute and we'll start. Okay. Okay, let's do something. Artists people, why they're here? Okay. input circuit. So we may have current, we may have voltages. They are at levels, if it's secondary circuits of substation, 5 amps, 100 volts. If we do monitor, for example, solar system, something like this, so it may be 400 volts and so on, and on DC side up to 120 volts. So these signals we would like to process are high currents and quite high voltage. All these do not feed directly for digitalization, for sampling, and for DSP forward. So we need, how to say, interface circuit between high level signals and something in our internal electronics. So we need to convert the signals into levels suitable for processing. That's not all. We need insulation, and we always should think about EMC compatibility, because the signal make high current, high energy equipment, and may contain all kinds of noises and disturbances that cause faults in our electronics. So EMC, electromagnetic compatibility, also how to say, we cannot omit. So very start, easiest approach is with transformers. We can use simple steel core what with resistance. This is for current. Steel core transformer. This circuit as a result will produce voltage being some kind of radial current. Very easy, yeah? Current transformer or voltage transformer. Simple steel core transformer. Third easy approach. We will get, what we will get? We will get is level conversion, and we will get insulation. Transformer. Coils are insulated, and at here's what we have. Good level conversion. Not so easy, not so easy, yeah? That dog is digging. Not so easy. Where we need to look deeper, we need to think wider, and we need to understand what this circuit should be precise, and we need to take into account one more thing. It's a frequency response of this circuit. Why I'm started talking about precision? For power transformer, no one thinks about exact precise transformer ratio and what is real transfer between primary and secondary part. Here we need measurements. We don't care about economic efficiency, energy efficiency. We care, okay, it cannot be extremely expensive. It should be reasonable price, but we should think about error. If we take typical magnetizing loop of the steel cord, we will see something like this, yeah? It is not linear. Meaning what? If we have current transformer with primary 1 volt resistance I2, what we will see? It's a current transformer. It's when you speak about current circuit, think like they are powered from current source. General ideas from electrical machines are not working well here, because it's a specific area of current transformers. In case we are talking on current transformer, think about its substitution schematic. Resistance of primary winding, inductance of primary winding, something very small. You have massive idea. Inductance of secondary, resistance of secondary, load resistance. Here your voltage being coming out. Here signal you will process further. This is source, and this one is a magnetizing impedance, impedance of magnetizing circuit, non-linear. This part, non-linearity is presented with this resistance. It's not linear. If you look I1 effective value, secondary current flowing to load resistance. For ideal current transformer, it should be line targets of this is transformer rated. This should be in reality this is due to saturation of the steel core. Real point for protection, point of 10% error, and 10 point. The higher load resistance, if you increase load resistance, you will get this one a lot higher, this one a lot lower. So the lower load resistance, the higher will be linear, the higher knee point will move. But there is one tricky moment. If you want to design such circuit, you will need to find a balance. Balance of what? On one side, the lower load resistance, the lower load burden, the lower is load on the metal core, the longer near-linear part of the characteristic will be. But on the other hand, at one moment you see problem. What kind of problem? You will start something very testable will push you out from the low voltages, and it's noise from your own power supply. It sounds ridiculous, but if you try to operate on a very low voltage level at the input of ADC, you will see terrible thing. Noise from your own power supply will disturb your signal. So you cannot, in reality, you should maintain lower level of signal at processing tray, not lower than 1 volt, something like this. Lower level is lower level of signal. It's not obvious, but it's a fact. Is determined by signal to noise radio, and this noise comes from your own power supply. Tiny spikes. That means what you cannot. What's up? You have lower level of your signal, lower end of operation range. Something okay. Something like 5 or 10% of rate, something like 1 amp, half amp. This lower, at this lower level, lower current level, where your operation range starts. It's a bottom line. So this bottom line of signal processing should be above noise, expectable noise from your power supply. This determines lowest possible load for your current transformer. It's not obvious, it's a fact. Then one more moment. Here at the low end of characteristic, also non-linear present. Even good, it's good electrotechnical steels do have non-linearity at the center of magnetizing loop. Again, this means increase in error at a low signal. So, to evoke precise in this area, you should find a balance between burden you put your current transformer and amount of money you're ready to spend for a core. See, current transformer, this for metering, quite massive. Current part, this. See this core? It's made from stamped. No, this one. When you're looking for input transformer, for input current transformer, you start with what? With dynamic range. First, you need to understand there is a huge difference between protection oriented, how to say, signal channels and metering. Difference is in signal range. For protection, you need to have high level at 40. 40 from range. 40. Your higher range will be 40 in range. For metering and monitoring purposes, 1.52 raise E rate. But here your error margin is up to 10%. Here 0 to 0.5%. In case of metering, you need to ensure high precision but within small range. In case of protection, high dynamic range but easier on precision. Actually, you dance with something like this. It's an elbow tolerance field. Elbow errors field. When you start your design, you will see something like this. So here is the area of elbow tolerance. Outside, not permissible. What you need to do to increase your transformer precision? First, reduce leakage flux. What is steel config for typical low-end transformer? Second layer. Will go like this and so on. this type of transformer coil has significant leakage flux. And one more, when subjected to high current, they may vibrate. These gaps may change. So it's not a transformer of high precision, but this such design used. Some manufacturers do what? They immerse transformer in kind of epoxy resin to make them solid. So to make them less sensitive to vibration, more resistible to overcurrents. Such kind of transformers are cheap in manufacturing. They can be produced in Maes Valley. And they are not very precise. People do tricks in precision part to make them more precise. But this type of transformer, I don't think it's usable, they are usable for metering, really. Another type of current transformers are made on a road course. This one here, if you look, it's made from strips, they call it, from steel ribbon. This type of core much better. Why? It has very low leakage flux. It will contain flux inside, and it's stable. What's done? Immerse in a hot compound, vacuum immerse, and then hot drying. And before, what is done by a good manufacturer? They perform thermocycling. After winded and welded at one point, this core goes through thermocycling when it's heated and slowly cooled. This makes steel structure uniform. This model, it's approximately, say, 10 times more expensive than assembled from the sheets. Because winding is relatively small. You need much more turns and turning on toroidal. It's a toroidal transformer. What's good in toroidal transformer? They have closed magnetic paths. But this toroidal transformer much more expensive in manufacturing. Also, it's relatively large. You can see one of the tricks when we speak on panel mounted devices like energy monitors, control systems for solar export, energy export interface. They do have connection on 400 volt side. For such connection, one of the lucrative things is to use, I call them transformers on a leash. Idea, do I have example? Oh. cable coming into your panel, opening, they need a bigger opening. And wire, braided and coaxial wire comes from your device. Transform not to have entering. In general design, here should be interim one. Should be somewhere here, okay. General approach, here sits interim current transformer, from it current to your device, and on the input you have secondary, internal, auxiliary small current transformer. If your device is the only, to say, user of this current signal, you start thinking, why should I install second transformer? Why I just move input transformer of my device directly to sit on the connection cable. Transformer on the leash. The steering goes directly into my device. And insulation, what ensures insulation? Actually, you see, there is nothing here. Bare wire. It can be something, some kind of protective shell. But main insulation, cable. How to say, I call them transformer on a leash, transformer with a tail. Move your transformer out from your case on, because we have AMC problem, it should be coaxial cable, and allow it to sit on the 04 cable. What will be a negative side? On negative side, you need, because if you need precision, you need an interrupted core. This one is top range, maybe core made from stamped discs. Less expensive model will have core of stamped disc. But anyway, if you use this idea transformer on a leash, you need core large enough to fit cable. Meaning what? Losses in the steel. You will have, you will seek for balance because you will have losses in this quite large core. Right. Oh, I have one appears, it's a current transformer, but inside a very suspicious. Cheapest version of such transformer are made on powder core. Plastics mixed with magnetic powder and pressed together to form a ring. You can feel them by weight, they are lighter. Such of them still usable. But because there's always a danger of irregularity, not uniform distribution of powder within plastics, and anyway, they will have higher magnetic resistance. This is cheaper version. And pure disaster is attempt to use ferrite. Magnetic material designed for pulse transformers. This will be disaster because they have kind of rectangular magnetic loop. Not good. Okay, okay. What next? Where are my keys? So with current transformers, you always have a problem with saturation, limiting at the high end, and non-linearity at the low end. And low, you will always have an error because of leakage current. Piece of transformer core, it was wound from the steel ribbon, then cut and polished. Not so good as non-interrupted, but one of the way to fight for linearity, energy efficiency is not problem here. Problem here, precision, transform precision. In fight for precision, everything disappears. When we do fight for precision, we look at linearity. Since we don't need real load capability, we can use approach. Oh. Here coil made with, you see, 4 segments assembled together in a in a kind of clamp, creating a core. Such design can be used to create transformer with non-magnetic gap. Idea. Whoa. I'm drawing nonsense. Oops. Yeah, transformer with non-magnetic gap. Such design first appeared in audio transformers. Non-magnetic gaps reduce loading capability, but it's seriously increase linearity. This is done to make transformer more linear. Also, it shifts up its operation point. So, non-magnetic gap. Transformer with non-magnetic gap has lot capability. See, this steel is not linear. Non-magnetic gap is linear. So non-magnetic gap, but such transformers, mechanical, require serious work on mechanical design, or they will have error and temperature. Because expansion ratio of steel and non-magnetic material is different, you need thin, first it's balanced. Here, thin non-magnetic, how to say, insert a body of non-magnetic material to prevent temperature change. Because the expansion ratio of steel and non-magnetic material is different, it should have strong mechanical design. Such kind of transformer, I honestly, in real top design, I saw them only once in my life. It's got a real, true, high-end. I preserve sections of code, but where they are, somewhere. Transformers in magnetic gap to make magnetic system more linear, non-magnetic insert is incorporated. Transformer. Actually, for voltage transformer, it's not so large problems for currents. Next moment. Frequency response. Ordinary transformer with steel, if you analyze its range, transformer ratio as function of frequency appears going down. Strange. Problem of losses. Problem of losses in core. Non-magnetic insert helps. It's not change in transformation rate. It's change in losses in magnetizing circuit. Ordinary steel, electrotechnical steel, ensure operation range somewhere up to fifth harmonic. Somewhere up to 300 Hz, then losses are growing, and you'll see decrease from 30 to 50% in signal. They are not ordinary transformer steel, are not suitable for cases when you need to analyze high frequencies. Nickel-based alloys, transformer designs for high frequency rating, they are successor or derivative from phone transformers, easier to distinguish by design elliptical course, like this size elliptical course, designed derived from mostly field telephones. They are made from nickel-based alloys and are significant came with significantly higher price tag. What can also frequency, sorry. What to do in low frequency or DC part of the spectrum. And here starts circus. And the circus is with the circus is with resistors. I can use resistors, yeah, chance to get signal. But there is problem. I don't see what insulation. If this would be at ground level, I can do something like this. Direct usage of metering resistor this is for 1.5 kiloohms. It's precise, it's linear. No problem with leakage current. It's very good. Only one problem, how to insulate my electronics from high voltages. 1 second, I need to interrupt for a minute. I'll say closely. 1 second, I will back in a minute.
National Bibliotheca Maili. ക്ലാസ്സിന് ഒരു ക്ലാസ്സിലുണ്ട് അത് സമയത്തിനനുസരിച്ചല്ല. ഞാൻ തിരിഞ്ഞ് കേട്ടുണ്ടെങ്കിൽ ഈ ക്ലാസ് അടുത്ത ക്ലാസ്സിന് തിരിഞ്ഞ് അമ്മച്ചി എക്സൽ ചെയ്യുന്ന ഒരു പരിപാടിയാണ്. അമ്മച്ചി സമയം കൂടും എനിക്ക് കൂടെ ഇരിക്കും. എനിക്ക് അങ്ങോട്ട് കൂടെ ഇരിക്കണം. out.
sorry, it's too bit longer. We have meeting on financial issues. So, oops. Yeah, we have one here online. Microsoft will love me. Sorry, Microsoft. Okay, I need. Appears what I overspent my time. Okay, we can do it in details next time, but where the problem is with resistance? Key moment, insulation. You will be in problem, or okay, design you work with will be problem when, what we got? DC link. We have, it's a DC net. Very serious problem, what? Photovoltaics. Photovoltaics, 600, 1000 volts, up to 2000 volts. They are with small currents, but photovoltaics, this photovoltaic connected in series, operate at quite high voltages. And very serious point of concern, field current, excitation current of large machines. When we deal with large generator, it's generator protection or excitement system or power system stabilizers. When we need to deal with high current, the problem, voltages up to 2 kilovolts, currents up to 3000 amps. When you deal with excitement system of large machine, it's very challenging to take measurements from there. It's a real challenging thing. So, very special approach is needed when you deal with DC signal. When your device should operate. Now, one of the nowadays thing, DC networks, DC transformers, DC network, what kind of DC networks in industry, when you look at some manufacturing plant, you will see a lot of drivers with variable, with frequency inverters. And things like robots, conveyors, all kind of machinery with DC, DC stage, all this driving mechanic drive has a DC stage within. It's lucrative. Our university will work together with Daimler on one serious project. It's very lucrative to organize energy exchange on DC side. Because often we have what? One machine speeds up, I don't know, robot picks some piece for processing, or I don't know, it will pick something from a machine to send it to this machine center. Other machine this time slows down, it lays this already processed part. This without energy flow, machine what speeds up takes energy from network, machine what slows down just wasted on load resistance, on ballast. So energy wasted. It's very lucrative to organize energy flow on DC bus. But measuring that is very challenging because you need is hysteresis loop? Yeah, it's hysteresis, I draw a hysteresis loop. So it's very lucrative to organize energy flow, but it's challenging in measurement. When you take signal to your brain device, you need to measure high DC current with very specific requirements on AMC compatibility. Okay, I'm sorry, it's over. I needed to attend another meeting, so I'll continue next time.